reduce the sound underwater to help prevent detection of our submarines. So hopefully this is a exciting and interesting talk. And Aeriel, I'll let you get started since we're a little late. So.
No problem. Thank you, Rob. Thank you for the introduction. So sorry I'm not in person. There was a mix up with the Zoom and in person. Dan told me it was Zoom, but I didn't realize I could be in person. I'd have definitely trekked over to CEMAS. But anyway, today I'm going to talk about this old alloy called nickel aluminum bronze and how we've been using a lot of the tools at CEMAS to really kind of get a better understanding of the hardening and deformation mechanisms that occur in this material. Before I go on, I really would like to thank Veronica Mazanova and Milan and Joshi, who really worked a lot on this project. As you know, Milan and Veronica both went back to the Czech Republic, but before they did a lot of the work that you will see today. So I want to thank them before I go forward. So first, I'll start with the motivation and background for the work. I'll kind of go into some of the materials and methodologies that we've been using and really talk about how we've been using those tools to really understand the interactions between dislocation and second phase particles in the material and end with some kind of general conclusions. In general, nickel aluminum bronze is an alloy that was cast. As Rob alluded to, it's basically what your ship propellers are made out of on Navy alloys. But if you could imagine for the Navy, it's really important to be able to repair parts or print or design things on the ship, right? Because they're far away from mainland. Sometimes they're, in different countries. And one of the things I learned as a postdoc at NRL was that they wasted a lot of money. And so there were these doors that they would spend $250K on just to take a small part off the door when it failed because the company would not sell them just the part by itself. And so the ability for them to print things, whether they're as a Marine, whether you're in the field, or if you're a Navy, whether you're on a submarine or a ship, is very cost effective and time saving. So specifically, wire arc additive manufacturing is a way to print large scale structures. And we kind of discuss wire arc additive manufacturing as this new innovative thing, but it's really just welding in a way, right? But because of the nature of the printing, you can really build these large things using robotic arms. So as you can imagine, ship propellers are quite large. And so this is a way to build those components. So when you think of nickel aluminum bronze, it's this copper-based alloy. So it usually has additions of iron and manganese to really change, and those are usually done to change the phases that you get during processing. But it has excellent corrosion behavior, strength, and wear resistance. So if you think about things like ship propellers or underwater fasteners, it's a very good alloy that lasts a long time. It's actually quite old. So some of the first literature on nickel aluminum bronze was from the 50s. And a lot of it was really studying things like tensile behavior, understanding composition effects on that, as well as corrosion behavior. But when we think about it in today's time, it would be what we would consider a complex alloy. So a microstructurally complex alloy and a compositionally complex alloy. And a lot of it is because depending on how you change the composition, you can get very different phases. And some of the most important phases are these kappa phases. And so in general, these secondary kappa phases, about 5 different systems. They can vary in morphology. They can be lamellar, they can be globular, they can be spherical. They're mostly iron or nickel based. And we'll talk a little bit about them going forward. And it's very well understood that the microstructure and the mechanical properties depend very well much on the presence of these kappa phases as well as their distribution throughout the material. So they're very important in understanding deformation mechanisms. When we look at wire arc additive manufactured nickel aluminum bronze versus a cast and roll system, some of the things you can really see is that the microstructure is coarser. And one thing that happens in the cast and roll conditions is you get these large kind of globular asymmetrical type shape precipitates known as kappa 1. You do not see kappa 1 in the wire arc additive manufacturing condition, and that's because the solidification rate is much faster. And so you don't have the opportunity to precipitate out that phase. It's very good from a mechanical property standpoint because this is a brittle phase. And so a lot of crack initiation usually occurs at these large kappa 1 phases. Another thing you see are these lamellar type structures called kappa 3. And so kappa 3 is a nickel-based incoherent phase in the material. And then you can see kappa 2 here, which are these kind of larger globular phases that are also iron-based. And then there's kappa 4. And kappa 4 kind of sits within the matrix of the material. So just to kind of, I'll talk a lot about this later, but when we started on this project, our goal was to really see, okay, what is the fatigue behavior and how is that being driven by the observation of these different precipitate systems in the material? If we change the processing conditions in the wire arc phase, how do we change the microstructure? And then how does that influence things like fatigue? What we didn't expect was to really see or learn that kappa 4 plays such a large role in the hardening behavior and deformation behavior in these materials. So you can't see kappa 4 because it is a nanoscale phase. And so we need, of course, techniques with higher resolution. And of course, CEMAS has those. So when you think about the old papers, it's not that, they didn't want to understand. It's really that they didn't have the tools to understand. So it really shows the power of, the facilities at CEMAS and these microscopes to really be able to truly understand what is driving deformation and hardening and strength in these materials. And can we be using them in different ways as I'll talk a little bit about later? Can we be using them in different ways than more than ship propellers? Could they be used in different ways? So we'll talk a little bit about that. But from really having an understanding that the microstructure between the cast and roll condition and the wire arc additive condition is different, really the next step for us is to truly understand the mechanisms that control deformation and damage in these alloys. So next, I'll talk about some of the materials that we've been using. So specifically, we use there are different variations of nickel, aluminum, bronze alloys. Two elements that are really important in this is aluminum and nickel because they control, and iron, because they control the kappa phases that you get in the material. So this specific alloy had about 9% aluminum, 5% nickel, 3% iron, and 2% manganese. So what this is the wires composition. So this is wire arc additive manufacturing. And so that's what the composition of the wire is. If you ask me about the WAM conditions, I can't tell you too much about it because we get these made by a company called Gefertec, which is a German-based company that has pretty much perfected the printing process of nickel, aluminum, bronze, so they don't shear much. But this is really what the as received material looks like. So it has about a grain area of 40 microns squared. And so for us, what we do before we take any samples is we go through the thickness of each printed bar to really get a sense of how the microstructure changes through the thickness and along the length of the bar so that we really get an understanding of how these microstructures will influence the mechanical properties. And it's really because of the nature of AM. So you're reheating, remelting layers. And so you're getting different heat affected zones. Solidification rates may change because of this reheating and remelting. And so it is well known that you can get varying microstructure along the bar, especially along the thickness of the layers. And so for us, we kind of take most of our samples in the center of every bar because we know that the microstructure is pretty consistent in that region. And so it's just really keeping track of, what microstructure that we're looking at as we're doing mechanical testing. And so really, as I kind of talked about before, a lot of the limitations, even though this is a very old alloy and we don't really understand a lot about the dislocation interactions, a lot of it is just the tools that we had to really understand this behavior. So because CEMAS has STEM and things of that nature, we're really able to get on an atomic scale how deformation is proceeding in the material, and that helps better inform us on what is really driving the deformation behavior in the material. And then how do we design an additive manufacturing process that allows us to get this microstructure consistently throughout the material? Or if we're repairing a part on a ship, you know, do we have the right parameters to repair that part to have the same microstructure where we're getting really good behavior, really good ductility and strength? So next, I'll really talk about some of the dislocation precipitate interactions during tensile loading. So for us, we really wanted to start with getting an idea of the tensile behavior of the material so that we could provide better insight to what we see, what we would look for in fatigue. What we're learning is that the behaviors are actually quite different. And so I'll talk just a little bit about the fatigue behavior at the end, but it's not necessarily the same as the tensile behavior. But that was kind of our first introduction, was really understanding the stress strain behavior and better inform us as we start to do cyclic experiments. So what we did was we tested several samples to get a true understanding of the tensile behavior, and then we interrupted test either at the yield or at near the UTS to see how the changes in strain really changed the way dislocation behavior was progressing throughout the material. So we'll start with looking at the sample that was interrupted near the yield stress. And so this is the as deformed microstructure in this area. And really, this is the area of interest that we did a lot of deep characterization on to really get a true understanding of the deformation mechanisms. So one of the first things we noticed is that we had several different slip systems that were active during just the early stages of loading. So you can see here that there's 5 distinct planar slip bands oriented along the 111 planes. You can also see here that we have a stacking fault ribbon that is connecting 6 dissociated dislocations. Seeing the stacking fault ribbon for us was extremely interesting because, of course, we know that slip bands are going to occur in the material, but seeing this stacking fault ribbon was interesting because after combing through the literature for months, we had never seen someone report stacking fault formation in this material. So we had not seen stacking faults or any mention of stacking faults and even in some of the newer literature in the like 2023, 2020, we didn't see any reports of stacking faults. So that kind of was in the top of our head, like, hey, we're seeing stacking faults. Some interesting things are going on. Another thing we noticed was that you can see that Kappa 4, you can see a little bit here. I have better images, but you can see that there is this small, like nanoscale phase that's sitting in the matrix. But another thing we noticed was that we had these larger precipitates that were sitting along the grain boundary. And they'll become important too, because a lot of the old literature and even some of the newer literature were reporting these as a phase called Kappa 5, which is a heat treat phase. And what we've learned through extensive STEM is that is not Kappa 5. It's really this composite structure that's forming during the additive manufacturing process. But nonetheless, it has a Kappa 4 core, and we'll talk a little bit about that later. But regardless, you can see that the deformation is really constricted within the grain. You don't really see a lot of transfer from grain to grain in the material, but we see some very interesting things that allow us to kind of as a precursor to what we should be looking for as we continue to go on. When we start to look deeper into the deformation, we see that we have a planar slip is dominant, and you can really start to see from the contrast, the coherency contrast, these Kappa 4 particles that we're talking about kind of sitting in the matrix. And you can see that the slip bands are either, dislocations are either narrowly missing the Kappa 4 or shearing through them in the matrix. If we take a closer look, so here is our Kappa 4 particle, we have our dislocations traveling along the primary slip system. We can see that the primary slip system shears through the particle, the coherent Kappa 4 particle. and it's better here. And then we can see that there's this secondary slip system. And the region here is really undistorted. So it lets us know that that dislocation does not intersect the secondary slip system, and that there's some interactions between the stress fields of those dislocations that's preventing that transmission. And so again, we're starting to see some of the hardening mechanisms that are occurring at these early stages of loading in the material. Now, if we take a closer look, so if you're familiar with center of symmetry analysis, what it's looking at is how the atomic positions are deviating. And so it's calculating this M sub n parameter. And so the higher that parameter is, the higher the deviation is in the atomic positions, which means you have some deviation in the stacking sequence. And so the lower that number is, right, then there is no deviation in the stacking sequence. So by performing this center of symmetry analysis, what we learned is that we have a full dislocation that's separated into two partials. It's not hard to believe. This is a copper-based alloy. And that the leading partial shears through the precipitate, leaving behind an intrinsic stacking fault. And what happens, and that we know from like looking at samples at higher plastic strains, is that the trailing partial stays behind. So it's almost stuck, pinned at the interface here. And they never actually, as we'll see in later images, they actually never recombine. So the stacking fault stays in the material. We also learned that we have these extended stacking faults. So we can see here on the out of the shear precipitate that we have this extrinsic stacking fault. And we'll talk a little bit about what we kind of think, what we think is happening to form extrinsic stacking faults in the material. Now, one thing I talked a little bit earlier was that we were seeing these kind of grain boundary precipitates in the material. And what we had learned from literature was that people were referring to this as this new phase called kappa 5. Through a lot of work, what we learned was that there was a zone of about 200 nanometers from the grain boundary that was depleted of these coherent kappa 4 particles. So you can kind of see here the coherency strain, or the coffee bean contrast that you normally see from coherent particles in the matrix. And you can see within this region that there aren't any of those precipitates, and that you have these very large kind of flat precipitates that are sitting in this zone. And what we learned was that those were quiescent kappa 4 particles. And that they did obstruct dislocation motion. And the reason why they obstructed dislocation motion is because they weren't just quiescent kappa 4 particles by themselves. They actually had the segregation of nickel and aluminum at the interface. So they were this shell-like structure with a kappa 4 core and a nickel aluminum segregated along the interface. This was not actually new. Even papers into the 70s had reported this, this coarsening and segregation of nickel and aluminum along the interface. And really, what we learned through looking through the literature is this actually was a heat treat phase that could happen at 350 degrees Celsius. And it was very interesting because in the wire arc additive manufacturing process, the chamber itself is kept at 350 degrees Celsius. And so it was right, we didn't plan that. It was right on with what older literature had saw, right? So we knew that this was a heat treat phase that was actually happening during the processing. And so in the wire arc processing procedure, if we're printing 10 bars, the first layer of each bar is printed, and then the second layer of each bar is printing. So because we're holding the chamber at 350 degrees Celsius until the last layer is printed for every bar, it's pretty much getting a heat treatment, right, as the printing process is progressing. And so basically what we were seeing was the coarsening of kappa 4 and the segregation of nickel and aluminum along the interface. When we took a closer look, so in general, coherent kappa 4s have the Nishiyama-Wasserman relationship with the alpha matrix. What we learned with this shell-like composite particle was that it created an 8-degree misorientation between the cubic axes of the matrix and the composite. So it deviated from this Nishiyama-Wasserman relationship. And so what we learned through some of the more characterization that we did was that this did hinder dislocation motion. Now, does it have a large effect on hardening? Not so much, right? It's very few of them. And they are really a few of them at each boundary as you go along. But it was an important finding because A, it wasn't Kappa 5, which people had said it was. And it wasn't Kappa 2 either. And so Kappa 2 is another iron-based phase that people, because of the kind of globular shape, will sometimes just say, oh, it's globular, so it must be Kappa 2. What this showed us was that all of these things in literature that had been reported as Kappa 5 and Kappa 2 probably is just this kind of shell-like composite structure. And so then what we really wanted to see was, okay, as we progress to higher levels of plastic strain, then what is happening in the microstructure? So we used EBSD to really see where we had a grain that we knew had multiple slip systems that were active in the material. And so one of the things we wanted to see was where is strain localizing? So we use EBSD, of course, to look at how the orientation was changing from region to region through the kernel average misorientation technique. And what we learned is that majority of what we're seeing is strain localization within the alpha grains, which isn't hard to believe. I showed you some of the stacking fault formation and planar slip in the grain, but then also along these inner dendritic regions where we know we have Kappa 2 and Kappa 3, there was high levels of misorientation. So in this material, we wanted to take a closer look at the other precipitate systems like Kappa 3 and Kappa 2. So when we looked at Kappa 3 is an incoherent lamellar phase, and we can see that there is this high elastic strain contrast along the interface of the precipitate, indicating that there is this localization of strain. And so because fatigue is really our overarching goal, is really to understand fatigue behavior, this let us know that this precipitate or the interdendritic zones themselves could be possible sites for crack initiation as we start to look at things like cyclic deformation. Another thing we noticed in the at the higher strains is that planar slip is dominant, right? That we do not see tons of cross slip in this way. And I should say, in the traditional sense of cross slip, we don't see a lot of it. And that planar slip is really being facilitated by glide plane softening. So you could imagine one dislocation goes through, it destroys, one partial goes through, it destroys the order, which makes it easier for other dislocations to follow along. And so you get just easily an easy path for slip throughout your matrix. It's important when you think about from a hardening mechanism because it's an easy path, as the dislocations approach the gain boundary, they start to pile up, right? And what we saw before in some of the earlier things we talked about was that deformation was really kind of constricted within these grains, and that we really weren't seeing a transfer of slip from grain to grain. Now, some of the work that Nathan is doing in fatigue, we actually do see some slip transfer from grain to grain. But in this specific case, we weren't really seeing a lot of transfer from region to region in the tensile category. But regardless, we have a lot of planar slip because we have a lot of Kappa 4 particles, right? We have a lot of particles that are being sheared throughout our matrix. And so all of this is helping facilitate this kind of glide plane or this planar slip that we're seeing in the material, which is interesting. So as we look closer at these higher levels of strain, what we can see, is that we have a lot of sheared Kappa 4 particles. So Kappa 4 is iron-based, so you can see that there are a lot of sheared particles. This is a very nice one here. And if we take a closer look, we can see that within these regions, we have extrinsic stacking faults. and intrinsic stacking faults, as we saw earlier, but something that we have that we did not have before are deformation twins, right? So at these high levels of strain, we're reaching the stress levels needed to form deformation twins in our material. And so stacking faults and twins are very important because they also help facilitate hardening behavior in the material. And so again, really understanding what is driving the strength in the material, but then also because we have a lot of easy paths for dislocation motion, also helping facilitate an increase in ductility in the material as well. So let's talk about why we might be getting stacking fault formation and twin formation. So in general, when we think about cross-lip, we think, okay, well, if we have two partials, right? The only way they can cross-lip is if they recombine. They have to recombine into a full dislocation and then they can cross-lip. So that's just the traditional sense of the mechanism of cross-lip. But what we've learned from other materials like TWIP steels, so, or some of the high entropy alloy work that Mike has done, is that you actually can get partials to cross-lip by forming a sessile stair-rod dislocation. So from a mechanistic point of view, you have a full dislocation that's dissociated into two partials. The leading partial shears the precipitate, the trailing partial, in some cases, gets stuck. So now we have an intrinsic stacking fault that is formed. As we keep progressing, we know from our material that we have activated secondary slip systems. So now we have a secondary slip system coming, and we have two partial dislocations. It's energetically unfavorable. So what the first partial does is it creates this sessile stair-rod dislocation here, and then it cross-slips to the plane above. And so that creates an extrinsic stacking fault. As we keep going at high levels of strain, we have more slip systems to be activated. So now we have another partial that's interacting with the extrinsic stacking fault and forming a three-layer twin. And so this is something that has been reported in TWIP steels as a way to form deformation twins from stacking fault formations in the material. And all of this is really important because this is a hardening mechanism. And so when we're seeing this increase in strength, there's a lot of ways that this is being driven, right? So we talked about that we have kappa 2 and kappa 3 that restrict dislocation motion in interdendritic zones. So that's contributing to hardening. We have some coherency hardening from our kappa 4. Kappa 4 is also facilitating planar slip. So dislocations have an easy path. They go to the grain boundary. We know they don't transmit through. And so that's hardening. So there are lots of hardening mechanisms that are happening in the material as well. It's just our kind of initial understanding that, oh, we have some precipitates that are blocking dislocation motion. So that must be why we have hardening in the material. And so what we found, and when we looked at the low cycle fatigue conditions, is you can kind of see this stair-rod dislocation cross-slip mechanism kind of in action, right? So we see some evidence. So this is in fatigue that we have this intrinsic stacking fault here from another system that's pretty much just interacted with the original ISF and created this extrinsic stacking fault. And so we're actually still investigating these. One thing that we also see in our low cycle fatigue experiments, and so these are tension compression, is slip reversibility. And we're still really investigating that because that's interesting to be getting slip reversibility when we don't get it. Those will be two different mechanisms as we're comparing that to the tensile behavior that we're seeing in the material. And so what the tools that CEMAS has allowed us to do, and the reason why I titled it kind of reviving an old alloy, is what the tools have allowed us to do is not necessarily say, okay, all of the people in the literature are wrong, because when we look at their mechanical properties and our mechanical properties, they're spot on. We actually have pretty much very similar mechanical properties, but it's really just not having the tools to truly investigate deformation mechanisms, right? To really truly understand in the microstructure what is contributing to this increase in hardening or strength that you get when you look at the wire arc condition compared to the coarser microstructure that you get in the cast condition. And also being able to have a lot of these tools allows us to see that these aren't like, these are not new phases. These phases have existed for time, but now we can really understand what is the misorientation when you have a coarsened capital 4. How does that influence dislocation motion in the material? And truly really being able to quantify these things that are happening during deformation. And so these tools are very important because, as I said before, if you think about it from a Navy aspect, if I'm on a ship and a part fails and I can just repair that part, using a wire, I have a microstructure that may not be able to carry loads that it would to stay at sea for another, 200 days, but it may be able to carry the loads to get me home, right? And so truly understanding the microstructure that you get from these processing conditions really allows you to use these materials in ways that you may not have thought about before in the applications. And so just in conclusion, what we found is that, the shearing of these capital 4 precipitates are very important to dislocation behavior, right? They facilitate planar slip. They allow hardening to happen in the material. So it's really kind of getting the balance between the ductility and strength that we're always trying to achieve. And that really what we think is that this Stair-rod cross-slip mechanism is really facilitating the formation of these extended stacking faults and deformation twins in the material, and that we do have these incoherent core shell-like precipitates with an iron aluminum core and nickel aluminum around the boundaries that also obstruct dislocation motion at the interface. So in conclusion, thank you. I'd like to thank the Office of Naval Research for funding some of this work, and I'll take any questions.
Thank you, Aeriel. Do we have any questions from the local audience, or if you're watching virtually, could you please put them in the chat? Aeriel, are you still there?
I'm here.
Okay. Oh, sorry. Yeah. There are no questions at the moment. Let me see, did anybody write something in for Joss?
Have you considered doing dislocation analysis using ACM-based techniques like electron channel compatibility?
I'll repeat that for you, Aeriel.
Okay.
Have you thought about using ECI in the SEM to see if you can index any of these dislocations or do dislocation analysis yet?
Yes, we actually
Are you
have. So
Okay.
some of the earlier work that Veronica did was using ECI. We actually published that like a year ago. And that's actually where we really started to see the extensive planar slip in the material. If we're honest, that kind of gave us an idea that something is happening in the matrix that is, we knew capital 4 was, highly distributed throughout the matrix, but there was something going on, and ECI was actually the first indication that there was something going on in the matrix because we saw just extensive planar slip. So yes, we have done ECI on this. And Nathan has done ECI as well. And when you look at the, he's done it for the fatigue specimen. That's how we really could see the continuous slip banding.
I think that might have been what Johan wanted to point out, is that you get a much larger field of view that can sometimes let you see things that you might not see in the TEM.
Yep, we have did it. Yep, we have done
Excellent. Any other ones?
I think Brian has a question.
Can you say that? I might have, but were there observed dislocation?
Yes.
Okay.
Yes, Brian, there are. I did not show it, but give me a minute and I will show it to you. Yes, when we did a closer look, you could see, I'll show it here. Let me share my screen. So you could see that these like, and I hope you can see my screen, that these shell-like precipitates did hinder dislocation motion. And if we go back to the original presentation, so if we go back to like when we were looking at the yield stage, this was basically what we were seeing, right? Here they are sitting near the boundary, and it was hard to tell here if this was an initiation point, because the curvature, there was definitely some relaxation, but either way, there you could definitely tell that they were preventing dislocation motion. So yes. Any other questions?
Anything else, Brian?
Yeah, that would be interesting, actually. I agree, to see using center symmetry to see. We didn't, because at the time we were focused so much on the Capel 4, that's really where we're spending a lot of our time. But Joshi is continuing a lot of the work that Milan and Veronica started. And that's something we're definitely, as you said, really looking at the other, not just even just the shell-like, but Kappa 3 and Kappa 2 as well, really getting an understanding of what's happening there.
Okay, Ariel, I think that's all we have. So I really appreciate you taking the time to present today.
Yeah, thank you.
Yeah. So with that, everyone knows there's another Beyond the Scope next month, I think. If you're not familiar, please visit the CEMAS website. And yeah, we look forward to seeing you in a month. Thanks, Ariel. Have a great day.